Hello everyone, welcome to Digital Media E10. So today we're going to talk about optics, and I figured that a great way to get today started was actually to have a little bit of a movie.
These television lenses start with a very precise design. A diamond blade slices up a block of specially selected optical glass, while coolant prevents the blade from burning it. The slices then go under a diamond drill, which cuts several puck-sized discs from one glass slice. The operator is careful to keep waste to a minimum. Optical glass costs up to $1,000 per kilogram. During the drilling, the optical glass sits on a thinner piece of glass covered with wax. As the wax is melted, the discs are easily pulled away. Next, a device spins one of the discs while a wheel overhead sculpts it into a lens. The operator checks each lens for chips, and this one was smooth. This tar-like substance is called pitch. The edges of the lenses have been built up with tape to contain the pitch. They completely coat the underside of the lens with it. Several pitch-covered lenses are now in a metal shell. A worker picks up a hot aluminum dome called a blocking body. He presses it onto the pitch-covered lenses, and the pitch melts onto it. Dousing it with water causes the pitch to harden, sealing the lenses to the blocking body. The blocking body is now upside down and acting as a holding device as it oscillates on a spinning grinding shell. The grinding makes the surface of the lenses uniform and smooth. They place a polisher on the lenses. It's lubricated with a very fine abrasive. For about an hour, the polisher oscillates while the block spins. Polishing makes the lenses smooth and transparent. It also gives them an even more curved profile. The lenses have been removed from the block, and it's time to cut the diameter down to size. Using a microscope, a technician centers a lens between two brass chucks. A diamond blade at the back cuts the lens as the technician monitors it. He's making sure the diameter and axis of the lens have a common center. Next, they group some lenses on round racks called planets. Their universe is a vacuum chamber. The technician closes the door, and the planets continue their orbit. Inside this vacuum, an electron beam evaporates coating materials. The vapor rises to give the lenses a protective coat. A computer monitors the rate of evaporation and the coating. But there's much more to come. Up next, this process really gets visual as all the pieces of the camera lens come together. The lenses have just spent 3 hours getting a protective finish. It's time to wipe away any residue and make sure they're perfect. This particular lens is concave. She covers it to protect it while she cleans and inspects the lens with the opposite profile, convex. Then the convex lens goes to another technician who places it in a holding device. He looks into a microscope and adjusts the position of the lens until it's optically centered. He uses wax to keep the lens from shifting in the holding device. They give the lens another cleaning. Each one must be absolutely spotless before they proceed to the next step. Otherwise, dust particles could become trapped within the optical system and affect image quality. Now that the surface of the convex lens is immaculate, she dabs optical cement onto the center of it. She gives the other concave lens a little more scrutiny before she cements it onto the convex lens. She applies pressure to spread the cement between the two lenses. Cementing them together means they'll be less likely to shift around in the lens barrel. She checks for dust one more time. Then it's under the microscope for an optical alignment of this double lens. Because the cement isn't yet dry, he can push the top lens around and adjust its position. Next, they prep the barrel that will hold the lenses. The technician traces out lettering using a stylus, attached to a sharp tool that engraves information onto the lens barrel. It prints technical details that will tell the photographer just what the lens will do. Things like focal length, the f number, and the size of the aperture opening. These reference points allow the user to pull a picture into focus at the desired magnification. Now they double check the design for this complex optical system and begin to pull all the pieces together. This singlet, or single lens, goes into the metal barrel first. Other lenses with various curvatures and dimensions follow. She places metal spacers between the lenses to separate them. Proper spacing will prevent aberrations in the image, such as blurring. Between installations, she covers the barrel with a piece of lint-free plastic because eliminating dust continues to be a necessity. One fleck could ruin this entire assembly. Using tweezers, she coaxes the last lens into the barrel. She installs a retaining ring to hold the stack of lenses down. Then she locks it into place. There's one final inspection. She examines the assembled optical lens from all angles. It takes a total of 6 weeks to make one of these optical lenses. And in the end, it's picture perfect.
Oof. All right, so this is a clip from a show called How It's Made, which is on the Discovery Channel here in the U.S. And if you haven't seen it yet, it's actually pretty fun and entertaining to watch. It covers not just, of course, lenses, but a wide variety of topics. Everything from hot dogs to kites, perhaps, to cars, and all sorts of stuff. So you can really delve deep into it. And I think I even saw Netflix has it. So Netflix does have it, but I'm not sure that's necessarily something you might want to binge watch. some of the common things that they do are all of those puns. They love to have like the thing that's being made on a pedestal in a park somewhere with lots of color filters, and it's really interesting. But after a little while of binge watching it, you don't want to know too much more about how your food is processed or anything along those lines. Now, that was just an introduction to today, when we're going to talk about optics. And lenses are only a small part of what we're going to be talking about today, though, and by small I mean large, but there are many components in addition to lenses that we might want to reference as well. Now, before we get into sort of the nitty-gritty of it all, I do just want to mention a couple of announcements. Of course, problem set 2 is due tonight at 11:59 p.m. Project 2 is ongoing and due next week. Problem set 3 is released today and due 2 weeks from now. So as you can tell, the problem sets tend not to take quite as much effort as the projects, or at least that's what we're targeting. We're targeting that you should spend more time on the projects than on the problem sets. So be sure that you plan the next few weeks accordingly. And of course, if you have any questions about any of these, then do email the staff at staff@dme10.org. Now, coming back to this idea of lenses, there's a few things that are sort of interesting that we might be able to learn from that video right off the bat. And one of them is that lenses are, in fact, pretty difficult to make. There are, for the most part, especially on the higher end, a lot of these lenses are still handmade, or at least multiple, like the final assembly is actually done by hand. And there is still mechanical devices that will create the lenses themselves, because that is rather difficult to do. But still, these lenses don't necessarily take a short amount of time to create, and also they don't take a small amount of time to engineer. It takes the product cycle for one of these can be years, designing and testing and redesigning and working out all of the kinks. And so one of the things that we find in photography is that the technology for lenses doesn't change as much or as frequently as the cameras themselves, the camera bodies themselves. And so what we typically find is that lenses retain their value for much longer than the camera bodies. So if you're just starting out and you want to get into a particular camera system, you may want to reevaluate your budget in terms of how you want to spend the money. Perhaps you don't necessarily want to spend all of your money on a camera up front, but instead invest in some higher quality lenses that will hold their value for much longer and allow you to continue using those even if you do decide to change the body in just a few years. And in fact, this is a really great thing to do in general. You can buy used lenses that still retain all of their properties, are still very robust, and are still very high quality at perhaps a slightly reduced cost to what you would find in the market, but you can use those for a couple of years, give it a try, see if it's something that you like, and actually turn around and resell that lens. There's times when you will only lose $25, $50 on a lens that costs hundreds of dollars, if not $1,000, because they hold their value so well. This is actually something that I've done. You'll see a couple of photos here where some of the lenses that I took the photos with, I bought used off Craigslist or off of some other reselling website, used it for a little while and then resold it, and it was, well, not necessarily making a profit. I didn't feel like I really lost a lot of money in that effort. And it's a great way to sort of experience a lot of different quality lenses as well. Now, sort of one of the other takeaways that you would probably find from that video is that our lens diagrams up until now have been extremely oversimplified. We've been using this sort of single lens system, or as they call it, a singlet, to represent the entirety of our lens. And for our purposes, that's really been fine so far, but it's important to realize that lenses are, of course, much more complicated systems. So this is a photograph that our own Shelley Westover actually took of the Canon 400 millimeter lens, f4, I believe? No, 2.8L. So this is a massive lens. This is not a small lens by any means, but you really get to see in this cutaway view all of the elements that go into it. And it's really kind of a fascinating look at the inside of one of these optical systems. Now, there are a few other things that are interesting about this, and that is that it is itself on a little stand, and we'll talk a little bit more about what that stand is. That's actually that's part of. It's not necessarily it's not fixed to the lens, but it is in some way a part of it, and we'll talk about why that is in just a few moments. And also what all of these, why this bigger lens is actually representative of being slightly higher magnification, or in this case, significantly higher magnification than what we had in the past. Now, just a couple of things to remember. The f number, of course, is equal to the focal length divided by the diameter. And we talked about this using this very simple diagram here, where the focal length was basically just this length here from this lens to the point where all of the rays converge. And we can sort of think of this in a similar way, despite the more complicated lenses. But really, all we need to think about is this in terms of our own computation for the f number. And the diameter here is also somewhat misleading because it is not necessarily the diameter of the lens itself, but rather of the aperture, which is another separate physical device inside of the lens that will actually move. It will actually stop down and close in order to reduce the amount of light actually entering into the system. Now, there's a couple of other things that we have completely ignored as well, and that is what this focal length actually represents. And the focal length is really just a matter of magnification, or for us photographers, we can think of it in terms of magnification. Really, optically speaking, it has to do with the power, what's called the power of the optical system, or how strongly the optical system will converge the rays. But in our case, we can really think of it in terms of magnification. If you start looking into other sorts of optical systems like telescopes or microscopes, for instance, you'll find that the definition of the focal length, while still is that idea of the power of it, you might find that the opposite would be true, especially in microscopes, where a smaller focal length will actually increase the magnification. But in our case, a longer focal length tends to mean that we have longer lenses, roughly. It's not exactly the length of the lens, but it's roughly the length of the lens. It's analogous. It's really a ratio in terms of the lens. And that indicates that we have a higher zoom factor or a higher magnification factor when a lens is focused at infinity. Now, all of this discussion also makes one other assumption as well, and that is that the focal length doesn't actually change. So if we have a lens that does support a changing focal length, that means we have a zoom lens. That means we can change the magnification power of that lens and therefore zoom in and out. But it's not always the case that lenses have the capability to change their zooms. So this lens, for example, is fixed focal length at 400 millimeters. And that generally means a couple of things. One of them is that the lens can be, despite what this looks like, a simpler design. That generally also means that it might be cheaper, maybe. It might be less heavy, maybe. It might be simpler or more optically perfect than would be a more complicated system that comes with the extra elements involved with a variable focal length. So there's a lot of advantages to prime lenses. Those are three of them, and they're not insignificant. If for the same price you could get a lens that is higher quality, that's perhaps a win in some ways. So these are important things, just like everything else in photography, that results in a compromise that we really want to consider. Now, how can we really think of these focal lengths? And actually, I noticed in the upcoming slide there's a small typo I want to fix. Okay. Now, how can we actually think of these focal lengths? So what does it actually mean for a lens to have a focal length of 400 millimeters? Well, generally, we talk about all of these focal lengths in terms of a reference, and that is a reference of a particular sensor size. And typically, the sensor size is the standard 35 millimeter film size or a full-frame sensor in a digital camera. And so a lot of the focal lengths that you're going to see in today's lecture are in terms of that, or in terms of a 35 millimeter standard photograph. And so we can really define three classes of focal lengths, or zoom levels, basically. We have a normal range, which hovers around 50 millimeters in this 35 millimeter equivalent. 50 millimeters is sort of approximately the same field of view that we would see as with our eyes. That's not always strictly true, but it is close enough in approximation that we can consider this a normal view. That's why it's called normal. It's kind of how we would view the world. Once we get down to about 35 millimeters and below, though, we start getting wider. What this means is we're essentially more zoomed out. And so we get a shot like this in the lower right, which is taken at an equivalent focal length of 14 millimeters, which is very, very low in terms of a focal length for these for lenses. And at the telephoto end or the long end, the opposite of wide is more zoomed in. We could say that these are the very high focal length lenses. So this lens that we saw in the previous slide, the 400 millimeter lens, falls squarely into, very far actually, into the telephoto range. It is very zoomed in. It's typically used for sports or wildlife or something where you need to be at a significant distance from your subject. This allows you to take quite a few very interesting shots. In the upper right, I had the pleasure of actually using, I think it was a 400 millimeter lens. No, wait. It was a 500 millimeter lens with a 1.4 teleconverter on it. Anyway, it ended up being like 800 millimeters. It was this enormous lens, and got a chance to use it in a park in Berkeley, and everybody was looking at us because we had these enormous, I mean, they were huge, these huge lenses. My poor little tripod didn't stand a chance to hold this thing up. It was so heavy. And that's part of the reason why it's kind of a little blurry. I had difficulty focusing, and also at the shutter speed of this particular photo, 10 seconds, it was really, really hard to not let any vibration change that photograph. But this is actually an important point that you might consider, and that is that the longer your lens, the more zoomed in you actually are, that means that any small amount of vibration will become more and more important. And so you might recall a rule of thumb that we talked about early on, which was that generally you can generally handhold your camera at shutter speeds 1 over the focal length of your camera, which means that as your focal length increases, you need a faster and faster shutter speed to capture that in a still without any motion blur. There's some difficulty here as well. It really depends. We're talking about 35 millimeter equivalent focal lengths, but your own capabilities, the weight of the camera, how much coffee you had that day, all of these are factors that will actually go into the true shutter speed that you can capture for a particular image. Now, it's important to realize that we can make another simplification with this focal length as well. As we actually say that we increase the focal length, it's basically like we are taking the center portion of our frame and blowing it up. But we're doing it in an optical way, so we're not losing any quality. If we did this in a digital form, so in other words, if I took a picture like this and I took the center portion of it and blew it up, you can imagine that I will lose some resolution as a result. I'm throwing away some pixels and I'm losing resolution as a result of that crop operation. But doing this optically then allows us to have a lot more pixels at our disposal. In fact, there is one thing that I do want to show you here, which is and many manufacturers have this sort of thing. This is a website from Canon. It's a little bit older now, but this actually does show us the differences in some of the focal lengths of a lot of lenses. So we can see here a 15 millimeter fisheye lens. Fisheye is just, it allows curvature in the reproduction of the image because it's so wide that it's very difficult to actually capture all of those rays in a straight way, in a straight form, in rectilinear form. So they allow some curvature to get even more expansive width or within or field of view within the shot. So as we actually zoom in, we can see how this image is. There's cheesy sound effects as well. Let's see if I can mute that. Oh, I can't mute it. But we can see essentially what happens, that we can get closer and closer to this thing as a result. So really, it's like we are taking the center portion of this image and blowing it up. But again, we're doing this optically, so we're doing this in as high of a quality as possible. We're not doing this digitally, which would require those enhance buttons that you see on CSI, and of course do not actually work, and it doesn't actually work in that way. You can't see the reflection of somebody. I think did this literally happen in a CSI where they caught somebody because on a security camera somebody's face was visible, but that wasn't the suspect, but it was the suspect was reflected in the eyeball, and they were able to enhance the eyeball. Maybe I'm exaggerating it a little bit, but not too much. Still, the point is that all of that is it doesn't work. It doesn't work that way. really doing it optically is what we want in the end. But it's important to realize this distinction of actually changing our focal length, which allows us to zoom in on an object, and actually changing our distance to that object. One of these actions changes our perspective. One of them doesn't. And this is a very important point that you should realize, is that in order to change our perspective to an object, we actually have to change our distance to it. We cannot just zoom in more and say that our perspective has changed. It really depends on how we want to define perspective, perhaps. Perhaps we're using it in the context of a crop. So if we're actually using it like this is an interesting perspective, this is an interesting way to view this particular scene, then sure, perhaps a modification in the focal length is adequate to actually say that we've changed our perspective in that context. But in a technical sense, we're not actually changing our perspective. Our perspective really has to deal with the appearance of the scene as we would see it. So as we actually get closer to things, their relative appearance, their relative size compared to other objects changes. So as I get closer to this table, for example, it appears to me that it's getting larger and larger and larger. As I move away from it, its appearance also happens to get smaller. But this happens, but it does it in a way, this perspective change actually means that we see these objects in a slightly different way. And let me show you what I mean by this. I have a sequence of images here that I found on the wonderful site digitalphotographyreview.com. They have a lot of reviews. I've mentioned them in the past. dpreview.com. They have a lot of reviews and also some tutorials, but this sequence of images, I think, really demonstrates very well what we actually want to demonstrate. So this is a photograph of a table with a black background and a salt and pepper shaker. Now, the red box is just there because it's going to be useful in a moment, but we've just digitally added that onto this particular image. Now, imagine what happens when I actually take the image within that red box and blow it up to be the same size as this original image. It's as though I had zoomed in on this image, right? And that's exactly the top two images here. We have taken an image on the upper left-hand corner, which is our original image. We've blown it up, and that is what it appears in the upper right. Now, assume for just a minute that we did some math, or maybe we just did some guess and check, and figured out precisely the focal length that was necessary to provide to us an equal field of view optically. In this case, whereas the original image was taken at with a 33 millimeter lens, this crop resulted in an image that provided to us an equivalent field of view as 80 millimeters. So we take off this 33 millimeter lens, put on our 80 millimeter lens, take another picture, we get this one in the lower left-hand corner of the screen. Now compare that one to the one in the upper right-hand corner of the screen. For all intents and purposes, they're identical, except maybe for some small changes in color or in the lighting, which is really not relevant to this conversation. But the thing that is relevant is that perhaps you notice that the one in the upper right does have some loss in resolution. So because we did sort of a digital enhance on this, because we actually took the center portion of this, blew it up to be the same size, it's not quite as good of a quality. This is the same thing that we've been talking about. We've done an optical zoom in the lower left-hand corner. We've done a digital zoom in the upper right-hand corner. Now, you'll notice that by zooming in, we haven't actually changed our perspective of this particular object. All of the lines, in particular, the thing to notice is that all of the lines that are within the table and all of the lines that make up the object itself appear in a similar way. If we actually want to change our perspective, which in our case we are defining as this way that we can actually view the objects in relative difference, or at least the construction of that object in relative difference, then we actually have to change our view of it or change our distance to it. So let's remove this 80 millimeter lens, put back on our 33 millimeter lens, and actually get closer to these objects. You can then see the result in the lower right-hand corner. So even though this image was painstakingly created to make it as close as possible to the other images, you can definitely tell a difference in the perspective itself. Most notably, the lines converge in a very different way in the table. The lines that make up the objects converge in a different way as well. And this is really the distinction that we're trying to make between changing our perspective to an object and changing our zoom or changing our focal length to this object. And that's kind of one of the important takeaways of today. So one of the things that we can say is that a telephoto lens, a long lens, actually compresses our perspective. One of the things that you should notice here is compare how far apart these two objects look. One is definitely in the tile behind the other one. But in this photo on the right, what we notice is that that distance is exaggerated. And this is really that perspective change that we're addressing. As opposed to using our telephoto lens, which compresses that apparent perspective, by actually moving closer to it and zooming out, are we altering our perspective and really exaggerating the change in this. Now imagine that we take this to its extreme, and we actually, as we're moving closer or farther away from this object, we're also changing our focal length to it. You can imagine that we get this sort of neat effect. And I have here another video, which is, I believe, from the movie Goodfellas. Oh man, I actually don't remember. It has now been so long. But I'll show this to you first. But essentially what is happening in this video is exactly the process that I described. It started out in such a way that the camera was positioned relatively close to the table and zoomed out, and then it's placed on a track, basically. And as they moved back, as the camera operator moved the camera back, they zoomed in a similar amount. So let's see if we can watch that again. Now pay in particular attention to the appearance of the table and the appearance of the background. What's happening is that this perspective is flattening. The background is flattening against the foreground. And this is that compression in the perspective that I was referring to just a moment ago. So let's see the beginning. This is the before. When we're very close to it, and all of these lines are very exaggerated, where we have a wide angle in this particular case, we can see, even though we know this is a right angle, it doesn't actually appear to be a right angle in the photo. But as we zoom out, or rather as we move away from this, oh my gosh, I'm having difficulty here. As we move away from the table, oh, this is going to be difficult. Okay, I'll just allow it to do its thing. As we move away from the table and zoom in on it, we notice a number of things, that these angles actually do start to become right angles, that the background now appears to be compressed against the foreground. And it looks as though the background is getting closer and closer and closer to us. It's altering our perspective. In this case, not just because we're zooming in, but also because we're changing our distance to this. Now, this is called the Hitchcock effect, I believe, and I think Alfred Hitchcock actually used this in a few of his movies. So this is not anything new necessarily, but it's sort of an interesting thing to think about. And even though we are a photography class and not a film class, this is still representative of these ideas that you should sort of take away about this particular, about perspective. So those are the main sort of takeaways. But this means that when we're using wide-angle lenses, and as a result of the way that they are designed, once we go beyond some particular focal length, in other words, once we go beyond the normal range and into the wide range, then in order for us to start to fit more and more of the scene, to fit more of a field of view within the same rectangle that makes up our sensor, the lenses have to do some distortion. And this is just really a result of the way that they're designed and in the process that's necessary to capture the scene with a wide field of view. It introduces some distortion to the image. And so you'll notice, especially when you use very wide angles, that if you place people on the edges of those of that particular scene, that they will look stretched in some way. So in this case, it's not very apparent, except that here at the bottom there is some stretching that's happened to this person in the shot. So some of the ways that you can fix these problems are to try to square up the angles as much as possible. Try not to introduce harsh angles into the image, especially when you're using wide wide lenses to try to reduce this problem, and also try not to put people in the edges of those scenes with very wide angles, because they will look distorted, and people will invariably, if you take a picture of them at a very wide angle and they're in the side, they will look so stretched and distorted that they will be very unhappy with you for the result of how they appear in that photo. Now, on the other hand, when we're actually talking about zooming in and having very long focal length and getting this compression in perspective, this can actually happen to an extreme degree when we're using really long lenses. So this is a lens that I set up in my hometown of El Paso. This is before I got rid of my Canon stuff. This was with a Canon lens, a 300 millimeter f4, I believe, and I put onto it a teleconverter. A teleconverter is just an extra optical device that increases the magnification and increases the focal length of that lens by some factor. In this case, the teleconverter was a 1.4 teleconverter, so it multiplies the focal length by a factor of 1.4. And because it was on a crop sensor, it further changes the apparent focal length. And we'll talk more about what this actually means later. But in the end, the equivalent 35 millimeter lens that I had, or the equivalent field of view, came out to about 670 millimeters. So this is an enormous, very long lens. And the picture itself isn't really all of that compelling, but I do want to make one point about this, and that is the extreme amount of compression that has happened to this perspective. So let me point out a couple of things about this image before I actually switch away from this particular slide. One is that there's some homes here in the very bottom of the screen. There seems to be a main street that goes up a little bit of an angle and then continues to stretch on and on and on past the whole range of stores until you get down to what appears to be this green valley. Okay? So let me show you now on a map where I actually took this picture. This was in El Paso. All right, so let's zoom in here. And do I even remember my own hometown? I'm not sure. Let's see. Zooming in. All right. The edge of this little road right here is where I took the photo. Okay, just sort of remember that. I tried to drop a little pin. Can I put a little pin? All right, nope. I don't know how to use the new Google Maps. All right, so again, where my mouse is at the moment is where I took the picture. So recall those homes that were at the very bottom of the screen. Those happened to be just across Mesa Hill, so those were some of the homes around here. Okay, so let's zoom out some more. So again, this is where I took the photo. Remember that main street? That is this street. That curve isn't really in the picture because it really starts, the photo itself really starts after that curve. So let's keep zooming out here. So again, I took the photo right about here where the mouse is. Right here, we took the picture. This was the little hill right here. It kept going past the freeway, which I didn't point out, but it was there. Keeps going until it turns into this little road. And this over here is, in fact, the valley. And then you go a little bit further, and in fact, it changes to the New Mexico and Mexico border. So the full distance of all of this that we actually saw in this photo was a distance of about 6.5 miles. This is a lot within this one image. 6.5 miles, that's about 11, 12 kilometers, something like that. So we have this huge amount of distance that's visible in this shot from those homes that were very close by through that major thoroughfare that goes all the way down. We can see the highway is up here. Let's see, where's that? The freeway is right here, where the mouse is, and then it continues down into the valley. And so it really has compressed that perspective. And imagine if we had taken this with a normal lens, we really would have, all of this would have just faded into the distance. So this is just sort of a neat thing that sort of you should take away, and that if you want to have that perspective of actually flattening your subject against the background, using a very long lens is certainly one way to do this. Now, some of the other takeaways from that video were that the lenses typically have data printed on them that tell you a lot about their focal length and their f numbers. And it really depends on the creation of the lens that impacts what data it's actually going to show, or rather, really the properties of that lens is going to dictate what we see on that lens. And so there's a variety of types of things that we will see. We might see some lenses that are zoom lenses and therefore have a range of focal lengths. We might see a prime lens that only has a single focal length. We might see some zoom lenses that have a range of f numbers. And so what do all of these things mean? So on the far left, we have a pentax lens that has, if we read along the edge of this, it says 1:4, and then in parentheses 22, and then a focal length. So without knowing the camera this goes on, we can't really tell if this focal length is for a standard 35 millimeter camera. I would suspect not. I suspect this is probably for a crop sensor. But basically, if you see this 1 colon and then some number, that represents the maximum aperture of this lens. So in this case, the maximum aperture of this lens throughout its zoom range is f4. What this means is that this lens is not capable, based on the maximum diameter of the aperture and its focal length, it is not possible of using f numbers that are below that value. f2.8 is out. f2 is out. It's not a limitation of the camera, it's a limitation of the lens. But it is somewhat nice that in this case, even though f4 is the limitation, that it is in fact f4 constantly throughout that zoom range. Occasionally you will see lenses, particularly those that are bundled with cameras by default, sort of the kit lenses as they're sometimes called, or the less expensive lenses. Occasionally what you'll see is that they are indeed zoom lenses, like this Canon one, Canon zoom lens, EFS, 18 to 55 millimeters, but that its maximum aperture varies with the focal length. So in this case, the maximum aperture at 18 millimeters is f3.5, and the maximum aperture at 55 millimeters is 5.6. So it starts out pretty bright at a very, when you're zoomed out, when you're at a very wide angle for this lens, but I bet very quickly as you start zooming in, you'll notice that that focal length actually, or rather the f number actually changes for this lens. So we can infer that there is some complexity here to actually enabling a constant f number throughout the zoom range for a lens. And in fact, what we see in the higher range lenses, the ones that are a little bit more expensive, are a couple of these things. One is, well, they're higher quality generally. Also, that for a zoom range, they also tend to have a constant f number throughout that entire zoom range. Now, just because it has that property doesn't mean that the lens is going to be high quality. And just because a lens is expensive also doesn't necessarily mean that it's going to be high quality. But we can sort of use that as a measure, as a way of inferring the quality of the lens. And in this case, this is one of Canon's L lenses with the red ring around it, which implies that it is considered top of the line for Canon. The 70-200 f4, by the way, if you have a Canon, is fantastic. I love that lens. It was the lens that I was clutching to as I sold all of my Canon stuff because it was one of my favorites. In particular, the IS version, the one with image stabilization, was just so good. It was this very nice combination of weight. But I think you will also find that in a wide variety of formats, the lenses that represent this range in the 35 millimeter equivalent focal lengths, 70-200, are very good lenses. They tend to have very high quality, and they're, I don't know, it's something about that focal length that's just so good. So we can glean then a couple of things from the data presented on these lenses. One of them is the maximum aperture provided by this lens. Now, rarely you will find the same data that's on this Pentax, which is in parentheses, as you can see on the left, also the minimum aperture. So whereas the maximum aperture is f4, the minimum aperture for this lens is f22. And you'll rarely see that printed on the lens itself. If you really want to know, you typically have to look up the specifications of the lens. Now there's another number as well, and we'll get to this in a little bit more detail later, but you'll notice that there is a little line with a little circle, and it has another number, and it has another length on it, 58 millimeters. This represents the filter size for that lens. We'll talk more about filters in just a few moments. So sort of one of the interesting takeaways then are that lenses really come in all sizes, and they're not strictly tied. If you measure your lens, it's not necessarily going to be equivalent to that lens's focal length. And likewise, if you actually change the zoom on the lens, it's not necessarily going to extend or retract the lens to change its focal length. Some of these elements are actually inside of the lens to actually change the focal length of that lens. And likewise, when we change the focus, sometimes that will actually cause an extension or retraction of the lens, but it doesn't necessarily have to. There are some lenses where both of those mechanisms are internal and the size of the lens is fixed no matter what zoom or what focus range you happen to be in. Now, I did mention before this idea of having this extra little this extra little stand for some of these lenses. This is a tripod collar that long lenses typically have. And the reason that long lenses have them is that once you get beyond a certain weight for the lens, the weight of the lens will exceed the weight of the camera itself. And so it really doesn't make a lot of sense to then connect the camera to a tripod if the vast majority of the weight is very far away. It's very far to the front of the camera. So typically for large lenses, especially those that exceed the weight of the camera, then you will mount the tripod instead to the lens because it will result in a much more balanced system, which will also reduce vibrations in your image. So if the lens comes with a tripod collar, and especially if you have a smaller camera, if you don't have one of the big monstrous ones, then generally it's a good thing for you to connect your tripod to the lens rather than connecting it directly to the camera. So cameras come in all shapes and sizes. There's typically different ranges of them, high quality ones like the L lenses, the Pro series from Olympus. A lot of them are differentiated not only by the quality but also the speed of their autofocus. There's a lot of things that really differentiate each of these things. But one of the important takeaways also is that the different manufacturers don't really matter too much. If you're trying to decide between, for example, Canon and Nikon, it's not really going to make too much of a difference. The quality in the highest quality versions of their lenses, I would say that they're pretty equivalent along the highest end portions of the range. There's, of course, little differences in each of the individual lenses, especially when you talk about kit lenses. For the longest time, Nikon had very high quality kit lenses, especially when compared to Canon, which had much weaker offerings. That's probably leveled out about now. And these manufacturers tend to sort of leapfrog each other in terms of technology and these sorts of things. So don't really worry about which camp you're in. It doesn't really matter which one you decide to go with in the end. Now, one of the other things that we talked about was background blur. And this is actually impacted by the optics in our lens. And really, in order to talk more about this in a reasonable way, we have to think a little bit more about how the image itself is captured. So we talked in the very first lecture about pixels and how we can create a bitmap to actually generate our image. And a bitmap is essentially just a grid of pixels that represent, or pixels that have different color values. And in combination, when we view them, they make a picture. And essentially, that is what our sensors are as well. They're essentially rows of pixels that in combination capture all of the light that's been focused by the lens, or not focused if it's out of focus, onto the sensor, captures and records that information into the sensor, or rather into the compact flash or the memory of the camera, and then allows you to view that at a later point. But imagine for just a moment that these pixels are not infinitely small. These pixels do, in fact, have some area. They do have some width, and they do have some height. Even though it is very, very small, it's fractions of the width of a human hair that make up an individual pixel. But just imagine for just a moment that we're talking about these pixels that do have width and do have height. And when we look at a picture on our computer screen, especially at 100%, we can look at, and again, this is a little bit of a white lie, we're essentially looking at the individual pixels in our sensor. So think about that for just a moment and what that means for focus. What this essentially means for focus is that if the lens was able to take a point of light, let's say you had a completely dark room and you had just an infinitely small point of light that the lens focused onto your sensor, if it was actually able to focus that point of light into a size of the pixel that was exactly 1 pixel, then that will look sharp. You can look at that image on your computer at 100%, full size. It will represent 1 pixel and it will look totally, completely sharp. But imagine it was out of focus, and you've seen out of focus areas. They look a little bit blurry. So what happens if it was just out of focus enough, or if the optical system didn't have enough quality to focus it to a single point, but instead it took not just 1 but 2 pixels or 4 pixels. It really focused it onto neighboring areas as well. From a zoom level, that when you're looking at the image itself on your computer, if you were to look at the whole image, that small, just a couple of pixels, you probably would still look pretty sharp. Once you zoom into that, look at it at 100%, you might start to be able to tell the difference between the first image, which was perfectly in focus on 1 pixel, and the second image, which wasn't. And this is precisely the idea, in a digital sense, behind the very unfortunately named term called the circle of confusion. I know it's called the circle of confusion, but don't let that immediately shut you off to the main idea, which is that it represents essentially a circle, or in our case, in our demonstration here, or in our discussion here, a pixel, the square representing the pixel, that if the camera, or rather if the lens is able to focus some point light that to some smaller value than that circle of confusion, then it is going to appear to be in focus. So in other words, there's really a range through which an image can be focused or not focused before it no longer appears in focus, before it no longer appears sharp and therefore no longer appears in focus on your camera. And so in essence, this is what the circle of confusion is. Now, when we actually dig deeper into this idea of the circle of confusion, it actually has a different meaning. It's not actually equal to the size of the pixel in a camera, but it in fact takes into account a lot of factors, including the final zoom level that you're going to actually look at your image, your distance to that final image. So in other words, the circle of confusion is going to be very different when you are looking at an image at 100% on your computer screen versus when you're looking at that image on a billboard that's really far away. Just for the same reason that the circle of confusion will matter, will be a different value for when you're looking at that image at 100% on your screen versus in a very small window on that same screen. As you make that image smaller, the apparent size of that image smaller, then the circle of confusion can in fact grow and allow things to be slightly more out of focus, to have a little bit more wiggle room for things to appear sharp. But for our discussions, for what matters for us, we can really kind of think of this circle of confusion as being defined as the size of our pixel, because that will help us talk about some of these other things in just a couple of slides. So you can realize that there is more complexity here that really deals with how we are viewing the image in the end, and this was especially true for film when you had to decide if you're going to print your film on a 4x6 photo, or if you're going to print it full size to some big poster and display it in your room or something along those lines, where it made a lot bigger difference. But we can really think of it in terms of the size of a pixel for now. So if we assume that we have a circle of confusion, we have this lens that's focusing these rays of light, as those rays reach a diameter or a distance that's smaller than the circle of confusion, then they will appear to be in focus, and they will continue along, they'll converge, and then they will continue along that path and start to diverge after their point of, once they've actually been in focus. So there's really this range that the circle of confusion defines through which things appear to be in focus in our image. So with this in mind, it becomes a lot easier to think about how an aperture might impact our background blur. We have here two lenses that are equivalent in terms of focal length, but what is different about them is their aperture, the size of their aperture. On the top system, we have maximum aperture for this lens. It's letting in as much light as possible, and the rays are converging, especially so. Again, this is a slight oversimplification because rays are entering the lens everywhere along it, but we're looking only at the outermost rays that are entering this lens to really hammer home this point. We're just ignoring those other rays for now. But by having this aperture at its maximum setting, the rays come in at a very sharp angle because of the power of this optical system, because of the focal length of this optical system. So as a result, the depth of focus for a given circle of confusion, which are these black solid lines here in this bottom system and again in the upper system, correspond to a depth of focus that is much narrower than when we stop down, than when we increase our f number, than when we decrease the size of our aperture. So decreasing the size of our aperture allows these rays to converge in a lot less harsh of an angle, and therefore extends our depth of focus. And this is really the idea behind this depth of focus. So the way that I'm defining depth of focus here is that this is behind the camera, this is behind the lens system within the camera itself. So the depth of focus does correspond to a depth of field outside of the system, which corresponds to what is actually in focus in the scene, but we're only looking at it from behind the lens, only in the context of the sensor itself, so that we can really use the circle of confusion as a way of hammering down this idea. So depth of focus really is not meant to confuse you. It's just what is in focus because it's within the size of the circle of confusion inside of the camera. So there's another point that we can take away from this as well. Recall way back in the first lecture. So now we've talked about exposure. We've had now a lot of the fundamental terminology. We can start talking about some of these more in-depth details. And very early on in the first lecture, I did a lot of hand waving and said, why is it that we can see the dust from our pinhole lens? And someone did, in fact, say the correct answer. Well, it's because the aperture is very small, but the reason that actually matters is that the light rays that are entering in from a very small lens become much more parallel. So if you imagine that we have a sensor right here, for example, just right in the middle of our depth of focus, and we have some dust on top of, just resting on top of that sensor, as these rays become more parallel, those rays actually cast a shadow from the dust onto the sensor. Now, if those rays were coming at much harsher angles, which would happen with a much wider aperture, because now rays will be coming from the extreme edges, that dust isn't going to have quite as much of a shadow on the sensor as it would in these smaller apertures. So hopefully now all of these ideas are in fact coming together. But there's a lot more. Oh, yes?
Just had a question. So are elements that are closer than the point of focus and are out of focus at an equal distance to elements that are behind the plane of focus at an equal distance, are they rendered differently? Do they look different in an image, or is the blur like identical but upside down?
So the question is, within the scene, if we have an object that is in focus, and then we have something else that's some distance in front of it, and another object that's that same distance behind it, are they rendered the same? So probably not, because because the depth of focus tends to extend further to infinity, depending on a number of factors. It tends to follow further to infinity the closer to infinity you actually are. So what I mean by that is that it tends to be the case that it is logarithmic in terms of what is actually in focus. So something that is some distance closer to you might appear to be less in focus than something that is that same distance away. Now, that's not always going to be the case, but it will be the case in some circumstances. So I would say that the short answer is no, that's not always going to be the case, that it is going to be rendered the same if it's the equal distance from the focus point. However, there will be exceptions to that, especially if you are using a very long lens that has a very high or that is focused very close. I bet it would sort of change the perception of that, and it would look pretty similar in terms of that focus. But I would say that more often than not, that's probably not the case. Okay, let's take a quick 4-minute break, and when we come back, we'll continue talking about optics. Everything after what?
So after it crosses through the point of focus,
Mhm.
the image is like flip-flopped, right?
Well, it's upside down, but it's not end over end backwards.
Yeah.
So maybe I don't understand
So
the question.
the out-of-focus elements, I was just wondering if they look different because of that, if they're flipped, right?
Well, it's only that the top is now the bottom, so that wouldn't have any bearing necessarily on the distance closer or further away from the lens, if that makes sense. It would, and even within the context of flipping the image, only if it's close, it really will only sort of impact it if it's closer to the edge of the field of view, I would say. So welcome back. So just as we were coming back, we had a question about, because the image is flipped, and this is actually true. So images that come through lenses do become flipped. The top becomes the bottom on these images. And it was an extension to an earlier question about how the depth of focus actually changes for objects in closer and farther away from the camera. But because it's only dealing with, but because we're only talking about flipping the image top to bottom and not necessarily changing the distance to objects within the frame, I don't think that changes the answer before. So coming back to this idea of background blur, now that we have a slightly, hopefully better understanding or more intuitive sense for what's happening within the camera, it's important to realize that practically speaking, we as photographers and the internet photographers especially really place a huge and heavy importance within the quality of the background blur. And this has a very specific name within the camera community, within the photographic community. You might see it as the word B-O-K-E-H and pronounced either bokeh or bokeh, depending on how you actually want to do it, but it really alludes to the quality of the background blur and not to the quantity of it. So when we're talking about bokeh, we're not talking about how much background blur we actually have, but instead how good of a quality it actually is within our image. And there's a lot of things to look out for in this case. One of them is how circular are the out-of-focus areas. So you'll notice that in the center of this image, especially as we get further back, you'll notice that these out-of-focus areas for these point sources of light are in fact pretty circular. But other things to look out for as well are how uniform are those circles? Do they have little halos involved with them? In this case, it's doesn't really have too much of a halo effect, but sometimes it will appear to be much darker in the inside compared to the outside or vice versa. And also a variety of other things, including the geometry and just the overall appearance of it. It's a very subjective idea to look at the bokeh in terms of this quality. But there's actually something interesting about this image in particular that I want to point out now, and we'll talk to at a later point in time, and that is that in the center of this image, we do in fact see these circular point sources of light. But as we get farther and farther to the edge, notice what happens to those circles. They seem to get a little elliptical, or they look almost like cat eyes. And we'll talk more about why this happens as we get on in the semester. But just sort of pay attention to this and realize that within your own image, it may not be consistent. The quality of that background blur may not actually be consistent everywhere within the image itself. Typically, what you'll find is that the center portion of your image is the highest quality in terms of every measure. How sharp it is, how well focused it is, and the quality reproduction of the color and the geometric distortions are all minimized at the very center. But as you get further and further away from the center and closer to the edges, you actually start to see many more artifacts with the lenses. So if you're looking for a problem with your lens, look in the corners. That's as far away from the center as you can possibly get. So if you're trying to justify buying a new one because your old lens, quote-unquote, sucks, take a look at this. This would be a throwaway lens in my book. No, I'm just kidding. I love this lens. This is my new 70-200, which is actually a 35-100. And I actually hadn't even noticed this until I was putting together this particular slide today. And then I was like, oh, well, that's too bad, but also a good moment to talk about in class. So this idea of the bokeh is what we're really concerned about. And this has a lot of impact on the result of our image. And so we can really identify some of the issues of it when we're dealing with point sources of light, so just individual lights that are very far away and very out of focus. And this is not just some big bulb or necessarily the sun, but it has to be something that's very small, so a small LED or a small light that you might have that can really make it as small of a point source as possible. So I want to show you some other examples. And by the way, if you're not too familiar with this, if you haven't really looked at the quality of the background blur before, I apologize, because this is going to ruin TV for you for a long time. In fact, it has still ruined TV for me. Take a look at this photo. On the left, we can see we have point sources of light. It all looks pretty great until we actually look at the bokeh of that out of focus area. So let me zoom in on this a little bit. And what are some of the things that you notice about the out of focus area in this image? So is it high quality? I mean, maybe not. But so I saw some people shaking their heads. Why not? Why is this not very high quality necessarily? Any ideas? It's not circular. So yeah, that's sort of one of the big ones. But what's really interesting is that there is some geometry to this, right? This is a 1, 2, 3, 4, 5, 6, 7-sided point that's not circular. So why is this happening? What's going on here? Well, recall that we have the aperture. The aperture is the thing that's blocking the light. And so when we have some point source of light that's very out of focus, what we are seeing is the shape of the aperture in this lens. So whereas in the previous photo, we actually had a circular aperture, which is probably the result of some number of leaves that are actually curved at the edges. And so as it stops down or opens up, it actually retains a relatively circular shape. In this lens, it had straight aperture blades, and we can count 7 of them. I bet if you go back and watch a lot of TV shows and you pay attention to the out-of-focus areas, you will start to count, hexagonal, that's a hexagonal aperture, or, oh, that one looks pretty nice, that's very circular. And you'll start to notice some of these things. I notice it for some reason. Every time I watch Battlestar Galactica, the reboot, the most recent one, I feel like I am always noticing this. And they have that like lovely film grain and stuff, and oh man, it's great, but at the same time, I'm like, 6 blades. But anyway, so this is, I mean, some people might argue, well, I kind of like the geometry of this. And in fact, what you will see is that some people will make a fake aperture. They will cut a little heart shape, for example, out of some cardboard, put it in front of their lens, and all of the out-of-focus areas, they'll adjust their lens so that it is intentionally out of focus, and all of the out-of-focus areas will then have a heart shape. And so you'll see a lot of wedding photographers, well, not a lot of, but some wedding photographers will think it's cute to have like a picture or two of this, where the out-of-focus areas are actually a heart shape. But again, you have to have a point source of light to really identify that geometric shape. As soon as you start having a lot of areas that are not point sources of light, they're just wide swaths of color, then you don't really get to see that. But what you do see is that this is a proxy for determining the quality of those other focus, those other types of areas that are just wide swaths of color. Typically, the reason that we want circular and very consistent and very well-defined circles, and by consistent I mean no haloing and that sort of thing, is because it does imply that we will get silky smooth background blurs, silky smooth bokeh out of those other more typical out-of-focus areas. Now on the right, we can see a particularly egregious example of bad background blur. These 2 photos on the right are 2 different exposures of the same scene, but one of them, the top one, is in fact in focus, and the bottom one is not. So what is going on here? So let me tell you a little bit about this top photo. This is a photo of the Prudential Center in Boston, but taken from across the river on the Cambridge side. And it was a very far distance, but it used, if you look at the data, if you look at the data in the upper right-hand corner, you can see that we are using probably the highest focal length that I've used on my camera ever, 2,000 millimeters. So a huge, huge lens. So what is going on here? Any ideas why my out of focus area would look like this? So it's not a circle anymore, so what shape is it? Is the first question to ask, which is a donut. And I said before that the shape of the aperture implies the shape of the out of focus areas. So why is it that it appears as though my out of focus areas are donuts? And in fact, it's cut off here, but we can see that everywhere there's just these sort of funky donut shapes. Yeah? Exactly, yeah. So it's a telescope that has a reflector on the inside. And these sorts of telescopes have a secondary mirror. They have a primary mirror that collects all of the light and bounces that to a secondary mirror, which is suspended in the center of the telescope. So essentially what we have is this huge cylindrical object. Looks like this. The light is coming in this way. It's being focused and being reflected, rather. And then we have another little mirror that's suspended here. And that is precisely what is going on. And then this little mirror has another little mirror or something that actually then allows you to see the image that's produced by this telescope. So this is nice because it actually extends the focal length of this telescope without making it too big. It actually makes the size a bit more manageable. But it does mean that our out of focus areas do have this interesting result. Now for telescopes, this doesn't matter, because think about what you're using telescopes for, which is to take photos of very far away objects with extremely high focal lengths. You're compressing the perspective of these things a great deal. If you look at photos of space, you might see a lot of stars, a lot of nebulas and galaxies and these sorts of things. But imagine taking this idea that we had just talked about earlier, this compressing the perspective due to high focal lengths, and thinking about this in terms of the extremely high focal lengths of a telescope. We're talking about compression in orders of magnitude larger in terms of light years. So a lot of these stars look like they're very close together, but in actuality, they can be very, very far apart in terms of their depth, their distance from us, not necessarily their distance horizontally on the image. And so that's just sort of another way that we can stitch all of the same idea together. But in this case, I took a picture because I thought it looked really cool before I had actually focused the telescope. And by the way, if you are so inclined and you do have a telescope or you're interested in astronomy, a number of telescopes do have adapters that allow you to connect the eyepiece of the telescope directly to a camera. That is what I used here. I was able to actually just connect the telescope directly to the camera and take as high of a quality picture as was possible. And what's really neat also is that even though this was taken from across the river, you can see, and in the original image, you can read the exit signs in this top floor of the Prudential. It's kind of a neat thing. All right, so what if you want to go the opposite direction? You actually want to eliminate your background blur. This is something that we'd alluded to earlier. We talked a bit about the hyperfocal distance, but really what this means is that it has a very specific definition, and that is that nearly everything is going to be in focus. And more specifically, what it means is that everything from, let's say you have the camera set to the hyperfocal distance, that means that that object, that distance away, is going to be in focus. So let's say the hyperfocal distance for your lens happens to be 10 feet. That means that everything from half that distance, so from 5 feet all the way to infinity, is going to be in focus. And how we can actually compute this, well, there's another lovely little equation, and we're not really going to spend too much time on this one because this is not the sort of thing where you're going to be out in the field and computing the hyperfocal distance by actually taking your focal length and squaring it and then dividing by your F number and multiplying that by the minimum circle of confusion, which is actually the definition here. But most likely you'll have some sort of a chart. And one of the websites, I actually forgot to see if this was still up, but one of the websites that was around for many, many years is called dofmaster.com, and they have a variety of things like charts online, and there's probably hyperfocal apps that you can download for your phone that actually allow you to input your camera, the lens you're using, the zoom range that you want, to try to compute what that hyperfocal distance is going to be. If you happen to have an old school lens, there's actually a really, really easy way to compute this. So on the left is an old school lens where we can see the F numbers and they're color coded. So F16 is this cyan is light blue, F11 is yellow, and so on. And as a result, we can see it's color-coded because it corresponds to these ranges of focal of depth of field on this band that exists on the lens itself. And so we can set the hyperfocal distance by setting some particular f number and setting one extreme of that to infinity, and then we'll notice that the opposite end is going to be some value, and we can actually see that the hyperfocal distance is that exact point. So in this case, it's set to the hyperfocal distance for f16, because everything from half of the focus distance, which is in this case is 6 feet, that's 6 meters rather. Everything from half of that, from 3 meters all the way up to infinity, is in fact in focus. So it's really easy when we had one of these old school manual lenses, and this is really one of the things that I think is lost on us now, because a lot of our lenses look like this. It only shows us really the center point of focus, or how far away that is actually going to be. And we actually would have to do the computation or bring up one of these apps or one of these tables that actually tells us what the range of depth of focus and depth of field is going to be in order to find out if we're using the hyperfocal distance. So that's pretty neat, and one of the things to watch out for. Generally, if you have a long lens, it's going to be very difficult for you to get anything useful out of the hyperfocal distance. Sometimes the hyperfocal distance will be hundreds of feet away, and that's not going to be very helpful for you. Generally, wide lenses with very small focal lengths and very high f numbers are going to make this a plausible scenario for you to take photographs using the hyperfocal distance. A couple of other things to go over. Image stabilization. There's a lot of different techniques for this. Basically what it does is it counters your movement as you hold the camera to try to make the scene a little bit more still. And it's very important to realize that what we're talking about is making the scene itself still, the motion due to your, freezing the motion due to your movement of the camera, and not freezing the motion of the objects in the scene. So if somebody's running by and you have a very long shutter speed, image stabilization is not going to freeze their image. If you have a long shutter speed and they're moving quickly across the frame, they will still appear blurry, but everything else might just be in focus. And there's multiple types of image stabilization. One is in the camera, and the sensor itself actually moves to counteract your motion. And a different type is actually in the lens, and it actually will move some lens element to try to counteract your motion. There's pros and cons to each. Some of the nice things about having the in-lens stabilization is that it allows you to see, if you have an SLR especially, it allows you to see the result of your image stabilization in the viewfinder. So as you're actually looking through the viewfinder, you will see the stabilized version, and that's actually a little bit jarring at first, but it's also kind of cool to have this very long lens and have it be very stabilized. Makes it a little bit easier for you to frame your exposure. And also, we could argue that it could be tuned a lot better to the lens. So the image stabilization can, in fact, be improved for that particular lens and try to counteract, especially for the focal length of that lens, and behave at its best. And also, if you happen to buy newer lenses, perhaps they'll have newer generation image stabilization capabilities. However, this does also mean that every time you buy a lens, if it doesn't have image stabilization, you're out of luck. And if it does have image stabilization, it generally will raise the cost of the lens overall. And so you'll probably spend more overall for this privilege, rather than if you have an in-body image stabilization, which would be overall cheaper because now all of your lenses have image stabilization. But we could argue that it is not specific to individual lenses, and in fact it is the case that it does in fact decrease efficiency, and it does in fact reduce effectiveness for certain focal length lenses that you connect to your camera. But in either case, it's a good technology to have. It does allow you to take longer shutter speed images with your camera. And generally you get about 3 or 4 stops. I think modern ones might even do like 4 or 5 stops, which is kind of impressive. And what this actually means is that if you take that rule of thumb, 1 over the focal length, you can now compute 3 or 4 stops difference there. And it really does seem, especially for modern image stabilization technologies, really does seem to be the case that we can have at least 3 stops of corrected motion. Now, some other types of lenses that are really kind of interesting and unfortunately are fairly out of the price range for most of us is a class of lenses called tilt-shift lenses. And tilt-shift lenses exist for a couple of systems, but mostly the big ones like Canon and Nikon, where you are most likely to find tilt-shift lenses. But it really does provide to us a lot of unique opportunities. Oh, if you don't have a system that allows for you to purchase a tilt-shift lens, you can use Project 2 as an excuse to build your own. So that's sort of one of the takeaways, that you can use some lenses and some piping and some other cool stuff and actually create a tilt-shift lens so that it actually does, and by the way, this is not broken, it's meant to look like this so that you can actually tilt the lens or shift the lens and get some interesting results. So there's a couple of ways that these are useful. One of them is for architectural photography, and another one really is for landscape photography. These are kind of the main two uses, but there's a wide variety of other uses as well. So let's take a look at sort of a normal perspective. Let's say that I take a standard lens, a lens that we're all very accustomed to, and I want to take a picture of this church. I'm like, oh, this looks like a sweet church. I want to take a picture of this, and I stand there with all the other tourists, and I point my camera up so that the whole thing is in the frame. I take a picture, and this happens. What's wrong with this picture? Well, maybe nothing, maybe everything, but I would say that one of the things that's wrong is that the perspective of the parallel lines is lost. We have these converging lines, whereas that is not actually how the building exists in real life. What we actually want is for these lines to be perfectly parallel, to be perfectly square, so that we can really appreciate the architecture and the geometry behind this building. So let's say that I took this photograph and I didn't have the capability of a tilt-shift lens. Let's say I don't have any of that, but I, in fact, continue to use a standard lens. How can I fix this problem? How can I make it so that I no longer have converging lines in this building? What's that? Yeah, so I could raise myself up, and so ultimately I think whether I raise myself up or whether I stay on the same level, I have to then make the camera, change the angle of the camera so that the lens is then perfectly parallel with this face, basically. So I have to make it so that I'm not taking a picture of this at an angle. But what happens as a result of this? Well, what happens is that if I tilt from the same position, I tilt my camera down and I zoom out a little bit so I still capture all of this image, what else am I capturing? Well, I'm capturing all of this ground level here, maybe my feet, but I'm losing a lot of my focal length. I'm losing a lot of the zoom, perhaps, that was used for detail. But this really is sort of like the quote-unquote poor man's tilt-shift lens. In fact, this is precisely the thing that I did to take a better photograph, what I think is a better photograph of this church. I, in fact, zoomed out a little bit, and I tried to get a little bit closer and then tried to make it squared up with it, and then just later on cropped out the portion of the image that I didn't care about. So how then does a tilt-shift lens actually help us out in this particular scenario? Well, essentially what it allows us to do is to shift the plane, the sensor plane, off axis ever so slightly. So let's assume that I go back to that original step where I now square up the whole system, but now whereas before I had the top half of my image be devoted to the church and the bottom half be devoted to my feet and to the ground, I can now shift the image up and actually allow me to take this photo at the focal length without needing any crop. And so this is essentially what happens in a tilt-shift lens when I use the shift capability. I am, in fact, changing the location of the sensor relative, and really what I'm doing is I'm changing I'm moving the position of the lens so that I can maintain this idea. So here, if I have the church, and this might be the ground here, with a tilt-shift lens, I essentially move the horizon down, which means that I could perhaps zoom in a little bit more, get a little bit closer, or something along those lines. That is what the shift capability of a tilt-shift lens does. So likewise, you can imagine that what the tilt might actually do is change relative to the sensor the tilt of the optical system. So this is slightly not correct, because what it looks like is that the lens is remaining fixed, but generally your camera is remaining fixed. But generally what is happening here is that whereas you might have two different points be focused onto upper and lower parts of your frame, and again, this is a vast oversimplification and perhaps even slightly wrong, what we're showing is that by tilting the lens relative to the sensor, if this is my sensor and this is my lens and I tilt the lens, I can essentially alter my depth of field so that no longer is it a plane that's parallel to my sensor, but now it can be something that is at an angle, which means that I could, if I shifted it, or rather tilted it in this direction, I could try to get everything within the plane in front of me, like a field of grass, for example, in focus, using a relatively large aperture. And in a similar way, I can use this to sort of exaggerate depth of field in the opposite direction, and you might see things like this, miniaturization techniques, which actually use the tilt portion of tilt-shift lens, but in the opposite direction. Rather than using it to try to make more in focus, or rather trying to change the plane of focus to be the ground, for example, I'm actually exaggerating it in the opposite direction. So this is just an example that I found online on Wikimedia, which has a lot of good open source things, because unfortunately I have not yet had access to a tilt-shift lens. All of these things we typically have to do either in software. It's possible to do this same effect in software, or to do like the shift in software as well. Basically just crop it out and hope for the best. Now just a couple more things to go over, which are filters. And there's a lot of filters that are available that can help enhance your photography. One of the most important things to pay attention to is the little filter icon on your lens. It tells you the diameter of the filter that you should purchase. And so this does in fact indicate a new symbol that we have seen, which is this filter size symbol. Whereas before we had the location of the sensor plane, which looks similar, but it's slightly different because it is in fact a circle with a vertical line. The filter is essentially like a knot, a null character. It's a 0 with a diagonal line through it. And so that's a small but subtle and important, subtle but important difference between the two. So there's a wide variety of filters available for your camera. Some of the ones that I think are really important or really recommended are two: neutral density and polarizer, and in particular circular polarizers. So neutral density filters basically decrease the amount of light very evenly that come into your camera. And the reason that we might want to do that is if you want to have a very long shutter speed in the middle of the day, for instance, or if you want to try to continue to use a very wide open aperture for some reason in the middle of the day. Perhaps you might want to do it to maintain your X-sync speed on your camera if you need to use your flash outside for fill flash or something along those lines. Neutral density can be very useful in this way. Neutral density filters come in a variety of what are called factors, and it basically represents the number of times slower shutter speed that you can get out of that particular filter. And so generally, you probably want to start out with a relatively strong neutral density filter, because almost all the time that you're using it, at least in my case, I was using it outside in bright daylight, and I really wanted to reduce my shutter speed by a vast quantity. There are other types of neutral density filters as well, like a graduated neutral density filter, which is essentially neutral density on one side and clear glass on the other, which would allow you to try to even out the tones of a landscape. So if you have a very bright sky, for example, and a very dark landscape, you can try to use the neutral density portion on the sky to try to make it less contrasty between the two and try to capture and even out some of the problems that you might have from a very high contrast scene like that. Now, moving on to polarizers, what's interesting about polarizers is that light, because of its behavior as a wave, can actually become polarized. And so what polarization actually means how nitty-gritty do we want to become? So basically, we have light that travels along in a particular wave, but this is somewhat misleading because really this is like an electric field, and there's another component as well that kind of moves likewise at a 90-degree angle to it. It is basically a magnetism component, an electrical component as it's actually propagating through. And what's fascinating is that if these two waves, so imagine that these two waves are operating at 90 degrees of each other along their direction of travel, if these two waves become in sync, what actually looks like their overall intensity appears to move in some particular direction. This would be polarized light in this case, if it actually looked like it was moving in some particular direction. Sometimes, though, if they're just slightly out of phase, it will actually appear to travel in a circular way. And so we can have these different types of polarization. We can have a linear polarization, and we can have a circular polarization. So why does all this matter? Well, there's different types of polarizers. There's linear polarizers, which allow us to impact the first kind of polarization. And generally what happens is that light that gets reflected off objects, like water, for instance, or like the ground when you're actually driving around, will actually become linearly polarized. And so if you have sunglasses, for instance, that are linearly polarized or that are polarized, what you might notice is that they block out some of the glare, because this is the reflected light that comes off of these objects. And if you actually wear your polarized glasses and tilt your head 90 degrees, you'll notice that some of the things that change are what is actually being subdued. Because the polarized light that's being bounced off will propagate in a particular direction, and it will block all waves that are not propagating in some particular direction. So the reason that so I didn't mention this yet, but there are multiple types of polarizers, linear and circular, but the one that we want most for cameras is a circular polarizer. What this essentially is a linear polarizer in the front with another element behind it that repolarizes the light in a circular fashion. And this is important for those of us that have cameras with autofocus and auto exposure, because they are in fact sensitive. Those electrical components that use exposure or that detect the light for auto exposure and for auto focus rely on polarized light. So you can in fact disable essentially your exposure metering and your autofocus if you happen to use a linearly polarized filter in the wrong orientation. So a circular polarizer for our context basically just removes that linearly polarized light, or removes those extra, that glare, for instance, and will then repolarize it in this circular way so that we can actually then use it in our cameras. What the end effect is multiple. One of them is that it has the effect of increasing contrast within our scene. Typically, when you attach a polarizer to your camera, it will screw on, but you can also rotate it freely. And you should actually rotate it and see what maximizes the contrast in your scene. So at the very top right, we have a no filter at all, and then this is no software modification whatsoever. And the bottom right is with a circular polarizer. We can see that it increases contrast between the sky and the clouds. It increases the contrast in the colors of the trees. And also what it happens to do, like I said before, is in fact change the perception of reflection. It can actually remove that polarized light that was polarized because it was reflected off some water, and we can then see a little bit more clearly the things that exist beneath. So the important takeaways here: neutral density is good stuff. You generally want those. You want to use, unless you want to use a graduated neutral density filter, just get one with a relatively high factor. And if you were to get a polarizer, you generally want a circular polarizer, which linearly polarizes, but then it repolarizes the light, or basically scatters it. Well, I don't want to say scatters, but it basically repolarizes it as circular so that your focus and your exposure continue to function. All right, so for the last few minutes, I did actually want to continue with those in-class critiques that we have. And this time we have Rob that submitted a photo for us, and I want to bring that up here. Rob, do you want to come on up and introduce the photo for us? So thank you. And so the photo will come right now.
So I wanted to submit this because I've always sort of struggled with landscapes, and either it's too much or too little or something. So I wanted to get some feedback on this landscape and see what I could improve. This was shot last weekend in the White Mountains along Franconia Ridge. This was shot on the northernmost mountain, which is Mount Lafayette, or just before that, south along the ridge. And you can actually see the ridge run along the next two mountaintops there. And it was almost perfectly blue sky, and I probably should have used a circular polarizer, but just was curious what I could improve.
What sort of modifications did you make?
So this was imported. This was imported into Lightroom. I added a little bit of extra contrast. I actually added a very small amount of neutral density filter on the sky because it was very, very close to the white point, and there was almost no color left. But adding a neutral density filter brought some of the color back in the sky. And then I added some additional saturation to bring out the reds, which were in some of the bushes that were turning red for fall. But because of the light, it was a bit washed out when I started.
So why? So it looks like you've selected a square aspect ratio.
Because all the cool kids use square format these days, and so if you want to be cool, you got to use square format. No, not really. I always go with kind of the wide landscape format for landscapes, and I wanted to try something different, and I also wanted to accentuate the curve of the mountain and kind of put that in a more interesting spot in the frame. And so because of that, I chose a square format.
So is this a ridge hike? I actually haven't been on.
Yep, it's Franconia Ridge. It's so part of the Franconia Notch.
Is this the path here along the ridge? Is that what's visible here?
That's one of the paths, but the path is actually where these hikers are, and it extends all the way down here. You can actually see it fade off into the distance and go along the next few mountaintops there.
Very cool. Any comments to get us started? John has one.
I'm just pointing out that people from Skype pointed out that it's a beautiful photo with very painterly feeling, and the tones and the colors are just fantastic. So the word they used was painterly, and a couple of people said that. So the Skype people approve.
It is very painterly, especially the horizon. So this is sort of an interesting software application of that very idea that we were talking about, the graduated neutral density. So I suppose you applied it to the sky and then diminished it for the base, for the bottom of the image.
And a lot of times when you apply it in post, the mountaintop actually became too dark. So then I added a second.
Sorry. Could you repeat that?
I applied it about halfway down the image, but then the tips of the mountain were darkened by the neutral density filter, so then I added a subtractive layer there to actually brighten up the tops of the mountains again.
Thank you.
Anybody else?
Comments. So I like to say a great deal. I don't know what I think about the square crop, because it really does feel like it comes from Instagram, and I love Instagram. I try to post there as much as I can. But I remember one time I did experiment with the same sort of idea of trying to kind of replicate a little bit that Instagram feel, and I didn't like it for my own image, just because I think part of a lot of, I think part of what Instagram is like an oversaturation of color and that sort of overdone filter feel to it. And this doesn't necessarily feel that way, but it does feel like it comes from Instagram. So it's interesting that it has that sort of like emotional attachment to it. It is really, I'm amazed how colorful it is, to be honest. It is so red down. It's amazing to think. I was this past weekend, not up in New Hampshire, but in Maine, and I didn't think it was even that have that much of an autumn color feel to the area. So it's a neat. So I'm conflicted about that aspect ratio. That's, and I don't really know how to resolve it. But conflicted isn't necessarily bad, right? Like conflicted might just mean that it's sort of forcing me to think about my own biases about the aspect ratio. What was on? So what portion of the image was this crop from? Oh wait, let me give this back to you.
So I cropped the left side of the image, which actually just falls off into more of a valley on that side. And really, every time I look at my landscape shots, I'm like, this is so boring. It's just like the normal mountains, normal landscape shot. I don't know. It was really more to just mix it up than to improve the aesthetic, because I think a classic, like, longer, wider landscape makes more sense for a landscape.
What do you mean by typical landscape? Or by a standard landscape shot? Because in some ways, this is that, right? It has the sun in it. It has the sky. You can see the horizon in the background. So in what ways is this a departure from that landscape photo?
I felt like the far side of the mountain, the way it fell off, it was just too much of a central focus on the mountain itself and less on the geometry of the trail, which is what I was trying to capture a bit more in this image by putting it really close to the edge of the left side of the frame. I thought that the trail was kind of, because it was, when I originally framed it, I put that edge of the trail at the rule of thirds, like, you know, like you're supposed to. And I thought it just looked too mechanical, it looked too normal, and it sort of lost sort of the geometry of the trail and made it more about the scene as a whole.
Well, it definitely does achieve that. It feels like the trail now frames it in a way. You have the curve along the bottom, and then it curves back right along the ridge. And that's kind of separated from this distance, from the horizon, the mountains in the distance. So that I like a great deal. That's really good. And did you experiment with taking the left side? So whereas this is sort of the focus on the uncropped right side of the image. So instead of looking at that, focusing more on the mountain itself?
I did. The why I chose to leave the far right side was really just the hikers that were right there. I always want to leave like a little bit of some kind of human element in there, and I thought it adds more of a sense of scale, and it shows like that it is a trail rather than it's just the tops of these mountains.
Was there a comment?
So I was wondering if you considered, because I like the color at the bottom. I really, in terms of what it is, but I'm not sure if it's working with everything else. So, even if I cut off the bottom part and even some of the top of the sky, I get a sense of the curve even more. So if I just cover it like this.
So let's see if we can.
I don't know if we have a big white piece of paper we could cover everything. Yeah, if you down more.
So this is not precisely it, but along these.
But even down more.
Down more.
No, up. Up. Like that. that starts to take on a, I don't know, maybe not, but I was just wondering if that's something to consider. Because there's something about the shape of the trail that becomes really important, at least from what I'm seeing. And also, could there be a possibility for an object or another person to lead you back to the trail? Because there's something about that curve coming back sort of wants to keep coming towards me, but what you give me is then sort of this long flat surface on the ground in the foreground. I don't know. That's just what comes. But the depth is amazing in this. It's just
the depth,
and
I really enjoy the depth of this
environment.
So I know you were looking at this higher thing, but I wonder if I was experimenting. I was also thinking of that, but as a result of what you were saying, but also cropping the top more aggressively, so almost removing a little bit more of the sun, and allowing the mountains to be the thing that it fades into. So just allow it to fade into more of the mountain. So almost, I'm not sure if this is exactly the crop that we want, but something more along these lines. But it does remove that sort of feeling of expanse that was there before. Oops. Oh gosh. Interesting.
Yeah, I always struggle with the crop on landscape. So
Yeah,
those are all, yeah,
very difficult. Great suggestions.
different ways to look at it.
Any other discussions or inputs about how we might alter this crop? All right. Well, Rob, thank you very much for allowing us to show your photo. And thank you all very much for coming. We will see you next week. Have a great week.